Okay, so let us begin with the tutorial 6 for week 6. Alright, so now this week's materials are mostly based on superconductivity, totally based on superconductivity, I'd say. Um, and again, there are some questions based on concepts and a few questions that are mathematical a little bit, but mostly there are conceptual questions, I'd say, on this assignment. Although if there is still time after we finish these 10 questions, then I would like to um, solve one or two extra questions that are mostly mathematical and based on the equations and concepts you learned in the same context of superconductivity. So, right, let me once again check if it is recording or not. Right, so let us begin then. Now, the first question is, which of the following expression explains the isotope effect in BCS superconductors? Okay, so we know that the straightforward answer, if you have to if you have to point it out, then the straightforward answer is that your TC is proportional to 1 by root over of m. So you can also say that your TC is proportional to 1 by m to the power alpha, where alpha is equal to half. That is why you have root over sign on the capital M, which is the isotopic mass in this case. And by this concept, you get that if you multiply these two and get these two on one side, then you just see that your TC is equal to some constant, because there is a proportionality term, so there will be a proportionality constant if you remove the proportionality sign and just put a simple equal to sign, right? So this is equal to TC equal to constant by atomic isotopic mass to the power of alpha, or in other words, you get TC into m to the power alpha equal to some constant, where Tc is the superconducting transition critical temperature above which the superconductor turns into normal material. M is the mass of the isotope, and alpha is the exponent value. To be specific, alpha value should be half or 0.5, but the general idea is this relation. Okay, so our answer will be answer number 3. That is also given as the right answer. So basically, you know about isotopic effect. You have learned it in the from the concept of BCS theory and superconductors. But just to elaborate on the idea a little bit, we can also look at, let's say, yeah. So this graph I have added here for the understanding of isotopic effect. That you can see that this is a graph of TC versus this is 1 by root over of A. Here A is nothing but the similar meaning as M. So in some textbooks they use A as the isotopic mass, and in some other textbooks they use M as the isotopic mass. So they both are equivalent basically. So if your TC into M to the power alpha equal to constant, okay, so basically your isotope effect, this is the general version, and I already told you that the isotope effect that was actually proved experimentally. So basically one is the theoretical idea and other is the experimental proof. So the experimentally it was seen for different materials that your TC actually goes as proportional to 1 by root over of n. So basically essentially this alpha exponent's value should be half or 0.5. So now this is verified from experiments, but the original isotope effect concept is that if you have isotopes of the same element, like let's say isotopes can be like, for example, you can just simply take an carbon atom, right? So carbon can be C612 or C613, right? So they both are isotopes of carbon. So this is a generic example. Do not think that this is the isotope effect of superconductivity, because carbon is not a superconductor, you know that. But this will be valid for some superconducting element and their isotopic variants. So basically, for a simple example, you already know about the fact that C12 and 13 are both isotopes of carbon element. And why are they called isotopes? Because that is also simply known that they have the same number of protons, which is the number 6 here, and it is also equal to the number of electrons present in the orbital of the atom. and their mass number is different. That means for one case it is 12 and the other case it is 13. That means mass number is a sum of the protons number plus neutrons number in the nucleus. So if your protons number is same, so for isotopes you can say that your neutrons number is different for both of the isotope variant. Like in this case, C612 has 6 neutrons and 6 protons, but C613 has 6 protons, which is same as 612, but it has 7 neutrons because the mass number is now 30. So that is how isotopes are defined. And let's say for superconducting elements, you can have isotopes of mercury. Mercury is the first discovered superconducting material by Camelding-Ons. The first material in which superconductivity property was discovered below 4.2 Kelvin. So you can take mercury as your element example, and you can know that mercury can have different isotopes based on the different mass number, which can be Hg198 like this one. There can also be Hg202 like this one. So there are many different isotopes of Hg present in the nature. So they all have the same proton number, but their mass number is different. So these things, so these numbers are called mass number, which can also be notified by A, or sometimes it is also denoted by M also. Okay, whatever notation you would like to use. And the idea is that your if the superconducting element has different isotopes with different mass number, and the transition temperature Tc, or the critical temperature Tc, beyond which if you heat the element will lose its superconductivity and turn into a normal metal. That transition temperature Tc has a dependence on the isotopic mass of the different isotopes. And what is that dependence? Is basically that Tc is proportional to 1 by m to the power alpha, where alpha is some particular exponent and m is the isotopic mass. Or in other words, there is an inversely proportional relation. That means if you somehow increase your mass number of the isotope, then your Tc will decrease, and if you decrease the mass number of the isotope, then your Tc is supposed to increase, right? And this is a conceptual idea, and it is experimentally shown or proven that for different superconducting material elements, your alpha value is closer to half or 0.5 in most of the cases. So this is proved from experiments. This is from experiment that is verified. The alpha value is 0.5, and this relation is the generic relation for this is the relation is the conceptual relation. Okay, and this because your this Tc is proportional to 1 by root over of m, that means Tc is some proportionality constant into 1 by root over of m, right? So if you think of your Tc in the y-axis, that means you think of your Tc as your y-axis value y, and if you think of your 1 by root over m, this total quantity, as your x-axis value or x, then the only relation you can find between them is like a y equal to mx kind of a relation. That means it is a straight line equation, right, where m is the constant. In this case, m is the slope of the straight line, and in this case this is the constant, proportionality constant, that you have right here. So this is basically analogous to the equation of a straight line, and that is how you can get this graph as a straight line, that your Tc and x-axis, when it is 1 by root over of a or 1 by root over of m, you see that the graph you get is a straight line, total straight line. If you effectively, this is experimental data. So for different isotope variants of mercury Hg, there is different isotopic mass, that 203, 202, 200, 200.6, 200.7, 199.7 and 198. So all of this they have been chosen, and their Tc has been measured, and it is seen that when you plot that Tc value with respect to 1 by root over of m in the x-axis, you get a straight line like that, effective straight line. And so basically this is experimentally proving the fact that actually your isotopic relation or isotope effect relation is valid for superconducting elements, that your Tc is proportional to 1 by root over of m, right? And in that case, so you get that one more thing you can notice, that as you decrease the mass, you are basically increasing the TC. That means if you notice these points, so this first point has an isotopic mass of 203.4, which is the largest isotopic mass amongst all these isotopes of mercury around here. And you can see that it has the lowest TC value, that is, this is around some 4.125 Kelvin, I think. Okay. But as you go further, that means if you increase the isotopic mass, like in this case it is for 202, and this is if you decrease the isotopic mass, that means 203 to 202, then 200.7, 200.6, 199.7 and 198. So basically you are decreasing the isotope mass of the mercury, and you see for the lowest isotopic mass, this is 198, you get the TC value as the highest. If you draw a straight line effectively around this point here, you see that it cuts the y-axis at around 4.175 Kelvin, right? Which is the largest TC amongst all the variants over here. So basically it proves the relation to be true also from the experiments, and it is tested on mercury, which is the first discovered superconducting element by Cayley-Holmes. Right. So this is a generic idea and the mathematical relation proven experimentally. But if you have to explain or understand what is the concept behind choosing this effect, like how are we supposed to know that isotopic effect would be valid for superconducting element? Why the TC has such a dependence on the isotopic mass? If you want to understand that, then you have to look at the physics of superconductivity deep inside the material with the lattice. That is what is happening. And if you just take a look at that, so I would like to draw a picture for you to better understand it. So basically you know that for superconductivity the most essential thing is a Cooper pair, right? So you know that superconductivity, in short I am writing it as SC, which means superconductivity, and the main base element of superconductivity to happen is a Cooper pair, which is nothing but two electrons of equal and opposite spin and equal and opposite momentum are pairing up with each other and forming a bosonic particle, which is like a Cooper pair, and this is basically coherent throughout the system, and this is actually making the system to have a dissipationless current flow and also all the superconducting properties that are needed. So basically Cooper pair is actually the main base thing of the superconductivity to happen. Now if you just remember how does the Cooper pair form, then you will understand why this isotopic effect is coming into the picture. So let us draw a picture that if you have a lattice of atoms like this, so if you have different ions which are like organized in a lattice structure, so it has a particular position and it is periodic, so it has lattice structure that the atoms are organized, and you have free electrons inside the system, right? The free electrons which can freely pass through the metal because they are free electrons, so they are not bound to any of the atoms, they are just free to, like a free electrons, you can understand. So this is one of the free electrons, and this is moving inside this lattice crystal of atoms like this in this direction. Now normally these lattice atoms which can be ions, positive ions, they are basically in ideal case they are fixed in their equilibrium positions, which are, in this case, this is the ideal case when the lattice atoms are fixed in the equilibrium position. But in real case they are not ideally fixed to their positions, but as soon as the electron comes in the vicinity of the atoms, so all the neighboring atoms that are closest to the electronic charge, because the neighboring atoms have a they have a positive charge, so basically they will be actually attracted towards the electron, right? So let me draw it somehow. So basically this is an ideal case where lattice ions are fixed at their positions unperturbed by the free electron passing through. Okay. But in real case, what will happen is that because these ions are basically mainly positively charged ions because they have electron shortage, so they will be attracted because there is a Coulomb's attraction happening between the electronic negative charge and the lattice ions positive charge. So whenever the electron is in a vicinity of the, like let's say uh, the electron's position is right now somewhat around here, so all the ions that are right in the vicinity of that electron will be attracted to move towards the electron. So basically it is getting perturbed by the electron passing through. So the next configuration will be like this. If you just zoom in this part, so all the other rest of the parts remains the same in the lattice because those are not getting perturbed. Only the perturbed portion, is focused and like will be shown in greater detail in the next picture. So the perturbed part is shown and the rest of the lattice will be just as the same as before, so I will not redraw it, right? So this portion will be like this, that if previous position of the ions were these in the lattice, those were their ideal unperturbed position, but now the electron is passing through in between and there is happening a Coulomb attraction between the between the opposite charges, so the ions are getting slightly attracted or perturbed from their ideal position and coming towards the electron, right? So let's say from this position they have shifted now to this position, so they have come closer and this is also shifted from their position. Okay, um, this is also shifted and this is also shifted, so they are all being shifted to the towards the electron and they have left their equilibrium positions, which were these dotted lines. Now as soon as this happens, so basically the electron that is passing through is kind of surrounded by a positive ion cloud. So these electron, because of these ions that are attracted towards it, so basically this electron is actually kind of surrounded by a positive ionic cloud because those ions are positive that are attracted towards the electron. So it is a positive ionic positive ionic cloud around the electron, um, which when there is a second electron that is coming through, so it is not like that you have only one electron passing through, right? Because obviously there are many free electrons in the system, so when the next electron comes in the picture, so it will not see another electron in front of it because now that other electron is covered in the cloud of the positive ions around it. So basically this second electron will see, second incident electron will see that there is a positive ion cloud in front of it, and as a basic nature that electronic negative charge will be weakly attracted towards a positive ionic cloud in a distance. So basically it is like two electrons. This first electron that is surrounded by the positive ionic cloud caused by the electrons attraction of the surrounding lattice atoms and perturbing them from the equilibrium position. So the second electron, so this is the electron number 1 and this is the electron number 2. Although you cannot distinguish electrons, they are identical particles, quantum particles identical to each other, but here for the simplicity of the explanation I am writing it to be 1 and 2, as if the first electron has caused the lattice disturbance by causing this positive ion cloud around it, and the second electron has just come into the picture in the next scenario, and it is seeing not this electron directly, but it is seeing it through a positive ionic shield around it. So basically there will be a attraction, it will be attracted to this electron or indirectly to this electron through this atomic positive ionic cloud, and two of them will make a pair. Okay, So, and also this condition is very important, that the spins of the two electrons will be equal and opposite to each other, and the momentum will also be equal and opposite to each other. So if it is k, it will be minus k. But that will be a discussion in in greater detail, so we will not discuss that here. But the only thing is that just like that, a Cooper pair gets formed, which is a coherent, um, which makes the system coherent throughout, and it actually gives rise to superconductivity in the system. Although this is not permanent, as soon as this electron passes through, so this effect of the electron's attraction on the surrounding positive ion lattice goes away also, and then it actually all again relaxes back to its earlier equilibrium position, right? So it is not a permanent scenario, but in between that case, this Cooper pair breaks and the next Cooper pair actually forms, because now that same electron will be moving forward to some other position and will be attracting the positive ion cloud towards it from the other position as well. So that's how the Cooper pairs keep getting formed, and this actually is through the disturbance of the ionic lattice around the free electron inside the system. So one thing is very certain, that your superconductivity is happening in the system through an electron-phonon interaction, because ultimately this phonon is basically the lattice vibration quantum unit. So whenever the free electron is passing through the ionic lattice, it is causing a disturbance or a perturbation in the surrounding lattice ions, right? So that is how we are called, that perturbation is kind of a vibration of the atoms. You can think of it like that, that it is kind of causing a vibration in the lattice atoms, and that vibration can be quantized, and that single quantum of that vibration, lattice vibration, which is a collective as a whole, but we can separate it into quantums of vibrations, and that one quanta is known as phonon. So basically, phonon is the reason why two electrons are weakly coupled to each other instead of being of equal charges. So there should be Coulomb repulsion, right? So both electrons are negative charges, so they cannot attract each other, but instead there should be strong repulsion between the equal charges by Coulomb's repulsion. But instead of that, there is still a pairing happening between these two electrons, only because these phonons are in the picture. So this lattice is kind of acting as an indirect glue between the two electrons to form a Cooper pair. So in brief, we say that electrons pair up instead of Coulomb repulsion due to phonon induced, or in other sense, lattice perturbation induced indirect and weak attraction between them and causes superconductivity. So as you have seen that the lattice has certainly a great role to play in the superconductivity phenomenon. It is not just about the electrons being transported, but the lattice has a huge role to play. Otherwise, only electrons cannot just pair up and form a Cooper pair, right? There should be a lattice vibration involved in the picture. And that brings us to the idea of isotope effect, that obviously if your lattice is playing a very important role, then it matters that what is the mass of the lattice atoms that are present in the lattice, which is in this case the M or A, whatever you may like to call it. But this mass of the isotope in the lattice atoms do actually matter in deciding the superconducting phenomena in the system. Mass of isotope in the lattice. How? Because you can see that superconductivity and the Cooper pairing is only happening when the lattice atoms, which are positive ions, are getting shifted or parted from their equilibrium position and coming towards the electron, helping it to form a positive ion cloud around it. And as soon as the electron passes, those ions again goes back and relaxes back to their equilibrium positions. So there has to be a flexibility or flexible movement back and forth of the positive ions of the lattice, which helps to create the Cooper pair, right? So very naturally, if the lattice isotope, if the atoms in the lattice has an isotope that has a lower mass, or the mass value is smaller, that means it is much more easier to flexibly move it, right? Move it from the equilibrium position. So if if a material's mass is smaller, that means its momentum is also small, and we can very easily shift it to whatever position we want. And if instead the mass is very large, then the momentum will also be very large. Just like we cannot move a large or heavier object very easily, but instead we can move a lighter object very easily. Just by the same idea, if you have your isotopic mass to be very large, then these lattice ions, which are of heavier mass, it is very difficult for them to shift from their equilibrium position to come attracted towards the electron, and then again when the electron passes to relax back to the equilibrium position. That flexibility is not present as much in the heavier atoms of the lattice. But instead, if the flexibility is much more, that means if the mass of the lattice atoms is not very huge, or if it has a lighter mass, then it is very easy for them to just move back and forth from their equilibrium position, and it is helping to form Cooper pair more effectively, and as a result the superconducting property is much more stronger, giving rise to a very high TC. That means as high your TC value is, that means you are getting superconductivity in a much easier and convenient way. That is what TC is there for, right? So the higher TC value you have, the greater temperature extent you can go without changing the superconductor material into a normal metal. So the higher the TC is, the better is the superconductivity in the system. That is why the lighter is the mass of the isotope in the super system, the greater value will be the TC value, or it will help superconductivity. So that is why you get your TC proportional to 1 by root over of m kind of a relation. So this square root is actually a power that can be guaranteed or verified from experiments only, but to just get an idea of the relation why it is inversely proportional and not directly proportional with the isotopic mass, this is only enough to understand that if the lattice atom surrounding the free electron is lighter in mass, then it is easier for them to shift from the equilibrium position and come attracted towards that electron, and as a result help us to create the positive ionic cloud around the first electron, so that when the second electron comes into the picture, it can feel a weak attractive interaction happening through the or via the positive ions of the lattice with the first incident electron, and forming a Cooper pair, giving rise to superconductivity in the system. So that means the lighter is the isotopic mass, the better is the chance of superconductivity in the system, or you get a higher TC value. That means you can go up to a higher temperature and still not convert it into a normal metal. But if you have a heavier mass isotope, that means the lattice atoms are much heavier, and they cannot just move flexibly from the equilibrium position very often, and as a result it will not help in causing a creating a Cooper pair, and it will not help in superconductivity. And to achieve superconductivity in those materials, you have to go to even lower temperature, because superconductivity is not coming naturally. So you have to go to even lower and lower temperatures, so that you can like seize all the thermal disturbances and everything, and you can actually somewhat gain the superconducting property in the system. But this is the ideal understanding, that how the TC of the superconducting element is dependent on the isotopic mass m, and this has an inversely proportional relation with m has a power alpha, and from experiments it is specified that alpha value is half or 0.5. So this is the idea of isotopic effect. So this is also a result of BCS theory that you have studied probably. So this is question number 1 that we have done. Now question number 2 is that which of the following statement is valid for phonons? One is that phonons have spin half, which is not true obviously. So let us take one after another so that we can get what property is valid for phonons and what property is not. So first option is obviously wrong, because phonons, just like photons of light. So phonons are basically lattice vibration. So these are collective vibrational, there are collective vibrational modes in the whole lattice, and if you can actually quantize that vibration in a single quanta, and that single quantum is known as phonon. So it is the like simplest unit of, you can say, lattice vibration is phonon. Just like you have lights, for light you have photon. Photon is the simplest single light quantum. Similarly, single lattice vibrational quantum is phonon. So obviously photon, phonon, all of them are not particles with spin half, but they have integer spin values, and which is mostly 1. Like phonon, your spin is 1 and not half, because you can just directly get the idea that in phonons, so basically it is a kind of a bosonic particle, you can say, because their spin is a not a half integer multiple of h cut, but it is an integer multiple of h cut. So these are their bosonic particles, and their spin value is equal to 1. Okay. So what are phonons? Phonons are basically quantized unit of lattice vibration in a collective mode. Quantized units of lattice vibration is called phonon, and it is a bosonic particle, so its spin is not half, so it is not true. Second is that it obeys Bose-Einstein statistics. Obviously it is true, so we take it off, and also the answer is true, so it is right. It is as I said, that its integer is not half integer multiple. That means it is not following a Fermi-Dirac statistic. It is not a fermion, but it is actually an integer multiple of half. That means that it has an integer s or spin value, and it obeys the Bose-Einstein statistics, because it is a bosonic particle. So this is right. Now also let us read out the third and fourth option, just to know and be sure that they are not the correct options for phonons. Third is that have momentum h nu by c, where c is the speed of light, nu is the phonon frequency, and h is the Planck's constant. So one thing is for sure, that you know that your energy can be written as h times nu, Planck constant time frequency, and you know that momenta lambda can be h by p. Sorry, not momenta, but the wavelength lambda can be h by p, or the momentum can be h by lambda, right? Now if you have light, so this option is already not true. You can directly see that, because there is a c value, c term, as the speed of light, but phonons are not quantized unit of light. It would have been true if we are talking about photons, but for phonons they are not related to light, they are related to lattice vibration. That is why you cannot use the speed to be the lattice, to be the light speed in this case. So c is the light speed, and it will not be valid for a problem like this. So this option is not true also, we have found out, right? And fourth is that represent vibration of individual atoms in a solid. This is also not true, because as I said that phonons are not individual atom vibration, but they are a collective vibration of the entire lattice, and this is a single most, like the most quantized, like simplest unit of that collective lattice vibration. This is a collective mode response that we are getting. It is not an individual vibration of atom in a solid, but it is a collective sort of a vibrations quantized unit. So this is not individual atoms, but phonons arise from collective vibration of all atoms in the solid. Right. So this question is also done. Then let us move on to question number 3. It is saying that which one of the following is false about BCA superconductors. Which one of the following is false about BCA superconductors? So again, it is a conceptual question. So we'll read the options one by one and choose our answer. So option 1 is that the superconducting property can be destroyed by the application of magnetic field and electric field. So this is of course true, obviously true. because you know that just like there is a TC or transition temperature, there is also a critical field. Just like critical temperature, there is also critical field value, which is in this case Hc. If H denotes the magnetic field, then Hc is the critical field value for the superconductor. So this is certain field that even if you are much below the critical temperature of the superconductor, that means you should be in the critical in the superconducting regime of the material. But still, if you keep on increasing the external magnetic field, and if you somehow reach beyond the critical field value of the material Hc, then you will start to see that the superconducting property it has lost, and this has turned into a normal metal. So you can think of it like this, that if this is your M versus H diagram, so you know that M versus H is magnetization versus field diagram, and in the superconducting state, which is a perfectly diamagnetic state, so superconducting state is a perfect diamagnetic state. That we know from the basic definition of superconductivity, that its resistance almost goes to zero to the measurable limit, and it becomes a perfect diamagnet when it becomes a superconductor. So a perfect diamagnet means your chi value is equal to -1. The susceptibility value chi dia is equal to -1, or your M by H, which is chi is basically a ratio of magnetization by magnetic field, equal to -1, or M equal to -H. That means your M by H relation for the superconducting state is a straight line with a negative slope, as I have drawn over here, that your M by H is a negative slope straight line, and as soon as your field value reaches the critical field Hc, so this is this line, then your magnetization becomes 0. So up to this line, which is H below Hc, this is a superconducting state, and for H greater than Hc, when it has crossed the critical point value, then it is a normal state. Okay, so basically you can see that the magnetization becomes 0 beyond Hc, because the thing has become non-magnetic like a normal metal, and it has no superconducting property left. No diamagnetism, no magnetization, nothing is left beyond Hc. So basically this is the idea, and the main idea is that superconductivity extinguishes when you apply the field or increase the field beyond a critical limit. That is because the Cooper pair, that is the main source of superconductivity, actually gets destroyed if you increase your field value beyond a certain critical point. So basically, kind of you can think of it like that Cooper pairs are formed of two electrons of equal and opposite spins, right? So if you apply a strong magnetic field which is beyond the critical value of the material, then that field will try to align both the spins along its direction. That means if your like magnetic field is along the plus z direction, and two electrons forming the Cooper pair, one is along the plus z and the other is along the minus z direction, which is the rule of forming Cooper pair, that the spin has to be opposite and equal. Then if you apply a strong enough magnetic field, then both the spins will be trying to be aligned to the same direction as the field itself, and that is why both the spins will be parallel to each other. As a result, the pair will be broken. So the Cooper pair will be broken. That is why the Cooper pair broken means that the superconductivity property has been destroyed. So that is why it is true that the option is true that a superconducting property can be destroyed by application of magnetic field. And also how electric field is basically that electric field is somehow equivalent to applying some kind of an electric potential across the sample and getting a current, right? So this is also doing the same thing, that even if you are below Tc, that means you are in the superconducting regime, but if you apply an electric field, that means you are giving a potential to the system. So basically if you reach a certain critical value of the current, let's say if your current density is J, then when J is beyond the critical limit, which is Jc, this is the critical current density, which can be in the system when you apply an electric potential in the system, or in other terms electric field, then there will be a certain current generated by that. So when that current is below the critical point value, then there is no problem and the system is still in superconducting state, given that your T is always much lower than Tc. But if you somehow exceed that Jc value or the critical current density value, then the Cooper pair will again be broken and the superconducting property will be lost, because the Jc is the limit of the superconductivity, just like Hc is the limit in terms of magnetic field to destroy superconductivity. So there are three properties that actually plays the role in this whole picture: Tc, Hc, and Jc. These are the three parameters to control superconductivity. When you control via the temperature and all the other parameters are absent, that means no field, no current is given, then as you increase the temperature beyond Tc, you lose superconductivity. But let's say if you are much below Tc, that means you are well in the superconducting zone, and still if you apply a field and keep on increasing the field value to finally exceed the critical value for the material, which is Hc, then you will lose superconductivity because you will be breaking the Cooper pair. And same goes for Jc, that if you apply a electric potential or electric field and produce a current to flow in the superconducting system, then even if you are much below Tc, once your current exceeds a certain critical value Jc, then you will lose all the superconductivity present in that system. Second option is that the transition temperature varies as the atom is substituted by its isotope. This is also true because you know that this is isotope effect, that your superconducting transition temperature or Tc goes like 1 by root over of m, where m is the isotopic mass. So this is obviously dependent on the isotopic mass. So this is also true. Third option is that the variations of critical temperature for BCS superconductor is given by Tc proportional to 1 by m, where m is the mass of the atom. So just by the look at it, you can see that this is wrong, because here the relation is given as Tc proportional to 1 by m. That means the power of m is equal to 1 here, but this is not true, because experimentally it is verified that the isotopic effect that is predicted for superconductors has a particular exponent value alpha, which is fixed to be 0.5 or half for almost all the materials. So this is a wrong relation that is given. So your correct option will be number 3, because we had to choose the false option. Also for number 4, it is said that the elastic properties, the crystal structure and the thermal expansion remains constant as a system becomes superconductor. This is also true, because superconductivity only changes the property of resistivity and the magnetism. That the system tends to have almost a zero resistance, or at least below the measurable limit, the resistance is so lower that we cannot measure it in our limits. So that is how we can effectively say the resistance has gone down to zero for the superconducting state. And the other thing is that it has become a perfect diamagnet. That means its M versus H relation is a negative slope value with a chi value of -1, perfect diamagnet. And rest of the things that are present as a property of the superconductor, like the structure, crystal structure, or some elastic properties, thermal expansion, those are unchanged by the transition from a superconductor and normal metal. So this is settled. Alright, so we have solved already 3 questions and we have 7 more questions to go. So we are in question number 4, which is about the specific heat expression for the superconductors. Then it is said that choose the correct expression for specific heat Cs in the superconducting state. So S in subscript means that we have to calculate or know the expression of specific heat in the superconducting state. That T is the temperature, Kb is the Boltzmann constant, and alpha and beta are constants. So the correct answer will be option number 1, because this is already probably mentioned in the lecture materials. That your superconducting specific heat goes like exponential of minus delta by kT, where delta is your superconducting gap value, kBT is basically Boltzmann constant times the temperature. Now the detailed calculation you can always access from the materials but to get the idea, that I have here some of the graphs that can show you both from experiments and just by theoretical knowledge how the graph should look like. So first of all, the normal electronic specific heat. So basically let me first say the actual nature of specific heat in most of the materials. That normally you know that a specific heat goes like some gamma T plus alpha T cube, right, where gamma T comes from the electronic contribution of the specific heat, okay, where gamma is Sommerfeld coefficient, electronic contribution to specific heat, and alpha T cube, this T cube term comes from the lattice contribution to specific heat. So that is how the generic specific heat relation looks like. But at low temperature, at very low temperature, this TQ part is not very dominantly present, but this gamma T part is mostly dominant. That means at low temperature, the lattice contributions become smaller and the electronic contribution as a result gets very dominant in the specific heat. So CT at low temperature is dominated by the electronic contribution gamma T. That means C versus T will be a linear relation for normal materials, right? So this is what that is seen in this graph, that electronic specific heat, it is only shown because in superconductivity you mostly deal with very low temperatures because most of the materials have a very low value of Tc. So more or less you can say generally you are in the electronic specific heat regime only. So here this CE or electronic specific heat is plotted against temperature. This is for normal material and you as a result get to see a straight line curve. That means if you this is CEN, that means it is a normal metal specific heat, and as a result it has no transition, no other properties. That means it is only a gamma T kind of a behavior, and the slope of this straight line will give you the value of gamma. But when you have a superconducting transition in this case, then the value nature becomes different. Like initially beyond Tc, you can see this is this is your Tc value of the material. Then beyond this Tc, when the material was still in the normal state regime, then the line was the graph nature was linear, which is this orange line, right? Here CES equal to CEN. That means in this case, the superconducting electronic specific heat is equal to normal metal electronic specific heat, and that is why it is a simple gamma T sort of a linear term because we are beyond Tc. But when you are crossing Tc and going to even lower temperature, that means you are actually coming into the superconducting regime, then you can see a very significant change. First thing is that you get a huge sharp jump in the specific heat, discontinuity in the specific heat right at the Tc. This is known from the idea of superconductivity, that the normal metal to superconductor transition is a phase transition which is of the second order phase transition. That is that at Tc, if the phase transition is of second order, then you know that the second derivative of the Gibbs free energy becomes discontinuous at the transition point. So you know that the Gibbs free energy, that means d, if you write the derivative of the Gibbs free energy, dg equal to minus s dt plus vdp. This is from the thermodynamic relations, and S is the entropy. So basically your S entropy is equal to minus dg dt, right? The first order derivative of Gibbs free energy with respect to temperature is your entropy. But what is the specific heat? If you remember, this is just dq dt, or in other words, this is T times Ts dt. That is because dq can be written as Tts, and you can write the whole thing as Tt multiplied by ds by dt. That means you need to take a derivative with respect to temperature of the entropy. Now, if your S is equal to minus dg dt, then it is simply minus T d2g dt2, because this is getting a second order derivative of Gibbs free energy. That means your specific heat is a second order derivative of Gibbs free energy. That means for a second order phase transition, at the transition point it will show a discontinuity or a jump. So that is what we can see here, that at Tc transition point where the phase transition happens, the signature comes in as a discontinuity or jump in the specific heat, that from following a straight line point over here, it jumps straight up to a very high value here. So this is a discontinuity that we can see at Tc in the specific heat, and this is related to the phase transition being of second order. And then again it falls down very sharply, and that fall is actually of the form of e to the power of minus delta by kBT, because here you are decreasing temperature, you are increasing 1 by T. That means you are again decreasing minus 1 by T in an exponential pattern. So this is an exponential fall of the specific heat right below Tc, and this is a superconducting specific heat value that we answered, that it is going like e to the power of minus delta by K. So in this is an experimental graph over here, where you can see this main graph is for, I think, C versus T, and the inside is for the C by T versus T square graph. Okay, so you can see from the inset first that C by T versus T square graph, that means if your specific heat has a form that C equal to gamma T plus the lattice contribution is given with a coefficient of beta in this case, so beta TQ plus some higher order terms that we would not know, but if they are present such term, then C by T goes like gamma plus beta T square plus some higher order terms, right? So that means your C by T versus T square, if you plot this as in the y-axis and this T square in the x-axis, then you have this beta as the slope of a straight line. That means you will get a straight line. Okay, so you will get a straight line, C by T versus T square. You get a straight line, and the slope gives you the beta value, the lattice contribution, and the intercept gives you the electronic contribution or Sommerfeld constant. So this is the intercept, that is equal to the Sommerfeld constant gamma, and there are all obviously higher order terms present. So in this case here you can see the experimental data are in the black dots, and it goes all the way up to here. So up to this point, this temperature, you can see this red line fits very nicely this experimental data. So this red line is a fit with the expression that C by T equal to gamma plus beta T square plus beta 5 T to the power 5. That means it is a generic structure of specific heat having all the electronic lattice contribution and the higher order terms, and the experimental data fits with the form very nicely. But from this point onward, you see that the experimental data deviates from the red line fit of this equation, but rather it goes up with a very sharp jump at this temperature, and then again it falls down very sharply. So if you zoom into this part only, if you zoom that in, so then you come to the main panel, that right at this point where this temperature was around 2.7 Kelvin, if you zoom in, you can see very accurately that this is at 2.7 Kelvin, and beyond this temperature, the specific heat value is different, and from here suddenly there is a very sharp jump in the specific heat that is coming, and then again it is exponentially falling down with the relation e to the power of minus delta by kV. And it has been seen for multiple such superconducting elements. Not only that, this is another example where both of the graphs have been plotted together. It is C in the y-axis and T in the x-axis. So you can see that this normal material has a this line. So there is an exponent. This experimental data is with the like dot points, and the line fit to it is given by the formula relation on the specific heat in this table. So you see that for normal material it goes like almost gamma T plus beta TQ plus higher order term. That is why initially it is linear at low temperature, and then again it has a very slight bend because it is taking care of the lattice contribution and the other higher order terms. But if your TC is of the material is sitting at 8.7 Kelvin, then if there is no other critical magnetic field or critical current density applied, then simply by going below TC you will be able to have a phase transition into a superconducting state. That is why whenever you are getting into a phase transition of second order, then from coming from this phase to this phase, this is a normal metal phase, and this is a normal metal phase, and this is a here below TC, this is a superconducting phase, and at this point of TC there is a phase transition happening. So there is a huge sharp jump, and then again it is falling down as a superconducting specific heat of C e to the power of minus delta by kV. So this is the original thing that we wanted to be clear about. So this is the specific heat formula for the superconductor. So this question is being done. Then question number 6 is that the temperature dependence of the critical field of a superconductor can be described approximately by which of the relations. Then again it is very commonly known from the lecture materials itself. So the option will be obviously BC T equal to BC 0 into 1 minus T by TC whole square. So basically if you plot a graph like this, this is your BCT, that is a critical magnetic field with respect to as a function of temperature, and the x-axis has temperature also. So at TC is this point and T equal to 0 is this point. So then at T equal to 0, we are here. So this point we mark as BC0. That means the BC value at T equal to 0. This is the y-axis value. And this is the x-axis value, which is TC, the superconducting transition temperature, where this BCT becomes 0 finally. Okay, so this is the whole relation. This is a quadratic form. That is why we get a plot like this. But to actually explain the physical significance is basically that if you put T equal to 0, that means you are at very low, almost 0 Kelvin temperature, then this relation becomes BC T equal to BC 0 into 1 minus 0 whole square. So this is just equal to BC 0. That means that if you are at 0 Kelvin temperature, then the critical field value at that temperature is the same as the critical field value at 0 temperature. That's why both of them are equal. But if you are at TC of the material, then your this term is equal to T by TC becomes 1. So your 1 minus 1 becomes 0. In that case, BCT equal to BC0 into 0 equal to 0. That means if you are sitting right at the critical temperature, then already by the temperature parameter you have gone into the normal metal regime, and you do not have to have a critical field value anymore to convert it from superconducting state to normal state. That is why your critical field value becomes 0 right at TC. And for all the intermediate temperature regimes where it is below TC but it is approaching TC, that is this regime, this relation will be valid, because as you are approaching towards TC, your critical field value decreases. That is very natural, because going towards TC means you are already losing superconducting property and turning into a normal metal. So there is no additional help required from the critical field to actually cause the transition, right? So this is the relation you have to follow, and remember that this is 1 minus T by TC whole square into BC0. Okay. Now, question number 5 is about the size of the Cooper pair is given by Vf is the Fermi velocity, Ev is the binding energy of the Cooper pair. Then what will be the size of the Cooper pair? That means the electrons, two electrons of equal and opposite spin and equal and opposite momentum actually bound together by a binding energy that is equal to Eb. Okay, so we have to calculate the size of the Cooper pair. So what could be done for that is basically, so basically your binding energy of the Cooper pair, that means the minimum energy that is required to actually break the Cooper pair, is Eb, right, as mentioned in the question. So the binding energy of the Cooper pair equals Eb. And you know that E, sometimes the energy can be written as h cut omega, where h cut equal to simply h by 2 pi, Planck's constant by 2 pi, and omega is nothing but 2 pi nu, or 2 pi times the simple frequency. So omega is the angular frequency and nu is the normal frequency. So the relation between both of them is also known that omega equal to 2 pi nu. Or let's say that this is equal to h cut. So you know that the V equal to omega r. That means if there is a circular kind of orbit present and the orbit's radius is r, then the angular velocity of the system, if it is omega, then at any point the velocity can be written as omega times r. So that is a basic understanding or the generic relation that is known. So this h cut is equal, h cut into omega means h cut into V by r. Or in other words, if this E is equal to EB, then this R can be, there is a possibility that this can be the effective length of the Cooper pair. So this EB times, let's say R equal to R naught in this case, equal to h cut Vf. So in this case, we use the velocity as the Fermi velocity because anyway the electrons that are actually capable of forming the Cooper pair are all in the plus minus h card omega t vicinity area of the Fermi level EF. So that is why you can approximately say that the electrons that are forming the Cooper pair can have actually a velocity that is much closer or approximately same as the Fermi velocity Vf. So that is why you replace it by Vf, and R naught is the effective size of the Cooper pair. That is why if you just multiply this, or if you just multiply this binding energy into the effective size of the Cooper pair, it is H cut Vf, or in other terms your R naught equal to H cut Vf by Eb. Here Vf is the Fermi velocity, Eb is the binding energy of the Cooper pair. So this is the effective size of the Cooper pair, R naught equal to H cut Vf by Eb. So this is the right answer. So I have to just copy paste the other of questions because I did not take the other questions in this case. So basically after question number 5, everything is being discussed already. Question number 6 is basically this question that the temperature dependence of the critical field Pc of a superconductor can be described by the approximate formula by okay, so this has also been discussed before, that this will be Pct equal to Bc0 into 1 minus T by Tc whole square, as we discussed earlier. I think this question is repeated, I think. Yes. So, right, so 1 second. We had 5 and 6. Okay, so 6 was already repeated. So 6 is already done. So we don't need to repeat this question. 6 is done. We start from 7. Which of the following are the properties of superconductors? So number 1 is they are diamagnetic in nature. Okay, so that is true because we know that we studied that superconductors are perfect diamagnets, and their chi-dia is equal to -1 in a superconducting state. So first one is true. Second one is they have zero resistivity. This is also true because in superconductivity rho tends to 0 E as you. So this is first one is true because superconducting state the diamagnetic susceptibility equal to -1 for superconductors. So they are perfect diamagnets. Second one is they have zero resistivity, means in superconducting state at T less than Tc, the resistivity rho tends to 0. That means the resistivity becomes so small that it is below the measurable limit of the resistivity. That is why we assume that they have zero resistivity in the superconducting state. Third is they have infinite conductivity. This is also true because if in the superconducting state resistivity tends to 0, that means the conductivity that is inversely proportional to the resistivity should be going to infinity. The superconductors, in the sense that they have a very high conductivity because in that state the dissipation goes to 0. So it is also true. And 4 is all of the above. So this is our correct answer because all the 3 of the properties we have to choose as true for the superconducting state, right? So the answer is all the above. Now question number 8 is consider the expression curl of Js equal to minus C by 4 pi lambda L square into B vector. So this is coming from the electrodynamic equations of the superconductor and direct to the London equation of superconductors. That is given in this example, this problem number 8 here. And it is said that using the definition B equal to curl of A, we can write Js equal to minus C by 4 pi lambda L square into A vector. Under the steady state, which of the following condition is required to write this condition? where c is the speed of light, lambda L equal to constant, Js is the current density, and A vector is the vector potential corresponding to magnetic field B vector. Okay, so basically, as I said that in superconducting state the electrodynamics is different. So there, to express those electrodynamics, the equation that is mostly used is called London's equation. Okay, so this equation and this equation, these are actually extracts from London equation that is valid for superconductors only. So how it is defined is that curl of J is equal to minus C by 4 pi lambda L square B vector. Note that here lambda L is a basically an effective length scale for this case, and um, actually this lambda L is a effective constant for this case. I think this value has as in London equation, this value has uh, ns mu naught by L squared sort of a. So actually, so I have to look at those formula once, and then I can give you the exact expression. So for now, let us assume that lambda L is a constant term over here, as we said. So yeah, so let me first write down the equation. So then go to this page that is written that curl of J is equal to minus C by 4 pi lambda L square B vector. So this is the equation number 1. Now this is then for superconductors. This is valid for superconductors. Okay, so the original equation was minus n square by m B vector, and basically we are replacing here that minus n square by m as minus c by 4 pi lambda n squared. So basically the sort of relation that is going on here, that this whole thing actually is represented in terms of this constant somehow. And although for the time being we do not need to bother about the values on the other side, rather we'll focus on the expression that we have to derive from it further, that it is said that if you use B equal to curl of A expression in equation number 1, that means B equal to curl of A in here. So what will happen is that curl of J is equal to minus C by 4 pi lambda L squared curl of A. We just replace B by curl of A. So since there is a curl sign on both the sides, so we can just get rid of that sign. That means we can just take this as we can just get rid of the curl from both the sides, and then we are only left with J is equal to minus C by 4 pi lambda L squared A vector. So this Js vector is basically the superconducting current density, or in other terms it is also known as spinning current density, and it is related to the vector potential like this. Okay, so then it is asked that under steady state which of the following condition is correct. So first of all, what is steady state? So it is asked that in the steady state we have to solve the equation. So steady state means it has no time variance, and in superconductor, steady state means where the current density is actually is not varying with time, right? So under the condition becomes, because it's the condition of steady state that we have said that it will not change with it will not have any variance under steady state. So that is why the superconducting string current density, if we take a divergence of that quantity, it will be equal to 0. Then because this front part is a constant, so this only leads us to divergence of A equal to 0. So this is the condition we end up for this thing to be valid, that um, divergence of Js equals 0 in the for this thing to be valid, that the system will be in steady state and this condition will be followed, the divergence of A equal to 0. This is also known as Coulomb gauge. This has to be satisfied. Okay, so up to this part we have covered then. Um, so we choose the answer to be the first one. Then question number 9 is the critical magnetic field is above is that above which number 1 is the material ceases to behave like a normal conductor. Um, so this is false, because we know that above the critical field the superconductor turns into a normal conductor, not the other way around. So it has to be that it ceases to behave like a superconductor. So the first one is not right. Second thing is that the material loses its superconductivity, which is true, because at the below above the critical field B greater than BC, so it actually the field when it crosses this limit, it actually breaks the Cooper pairs by aligning both the electrons in the Cooper pair in the same direction, electron spins in the Cooper pair in the same direction, and that is why the Cooper pair is broken. And at B greater than BC, the superconductivity is lost and it is transformed into a normal conductor. So answer option number 2 is right. Let us also read option number 3 and 4. 3 says that the material has a mixed normal superconducting state. This is incorrect. So whenever there is not anything mentioned very explicitly, so we assume that we are talking about type 1 superconductivity. Right? So we know that there are two types of superconductors, type 1 and type 2. Mostly type 1 is commonly known and already well understood from BCS theory. It can be explained by BCS theory. But type 2 is still not very well understood, and BCS theory do not explain the type 2 superconductors. So basically there is a few differences that happen between type 1 and type 2. Just like say for the case of critical field, we know that the type 1 superconductivity has a single critical field value, whereas type 2 has two different critical fields. That is, type 1 superconductors, and the second is type 2 superconductors. Okay. So for type 1 we have, this is M, this is H. Initially it is in the superconducting state, so chi equal to -1, perfect diamagnet. Then as soon as it reaches HC, that is it touches the critical field value, then this magnetization suddenly drops to 0. So this is m equal to 0. So this is your superconducting state up to this, and then above Hc these are called normal conductor state. Okay, so this is a single critical field value. And for type 2 superconductors, the thing is a bit different, that if you have, similarly, if you have m in this axis and h in the x-axis, you would see that first, for a brief time, it will also like type 1, it will also behave like a perfect diamagnet with chi equal to -1 slope. Then after a point in the field which is marked as Hc1, critical field 1, then the magnetization versus H is not like a simple negative slope straight line, but it starts to fall off, although not completely 0, and it has a different kind of behavior than 0, and suddenly and gradually it approaches to the 0 value, that it tends to touch the x-axis at some point. So we mark the point where it touches the x-axis at Hc2. So basically we have three different regimes created here. Below this point up to this point Hc1, this is a perfect or pure superconducting state, just as we have seen before in the type 1 case. Then above Hc2, that means from this point onwards, all the other higher values of H, this is basically a normal conductor state. Why? Because just like in this case, we have here the magnetization going to 0 with even if you increase the field. But between Hc1 and Hc2, this state is a very special state known as mixed state or vortex state. Okay. Why mixed or vortex? Because, so we mark it by this side, mixed or vortex, because below this Hc1 there was no like penetration of magnetic flux in the system, and it was behaving like a perfect diamagnet, which is a perfect superconducting state as well. So that is why it was actually repelling any kind of magnetic flux to enter inside the sample, and that is why you had a perfect diamagnetic situation. But above the Hc1 value, the magnetization does not suddenly or completely goes down to 0. That means it is not entirely entered into the non-magnetic regime, but there is a finite value of magnetization that is still left, which is gradually decreasing and finally going to 0 at Hc2. So basically, if you come to think of it, so between Hc1 and Hc2 is a regime where it is not in a perfect superconducting state, as well as it is not in a perfectly normal conductor state also. So it is kind of a mixture between both the states. That means it is a mixture of superconducting and normal conducting states. So you can think of it like there is still a superconducting background, but inside that superconducting background there are certain small parts where the flux actually can enter through those points, and actually those are called as vortices, which are basically small regimes of normal conductor inside a superconducting background. So this is also known as vortex state between Hc1 and Hc2. And then above Hc2, the magnetization completely goes to 0, so it becomes a non-magnetic normal conductor state. So mixed state is basically between Hc1 and Hc2, and it is only seen for type 1 kind of superconductors, type 2 kind of superconductors, sorry. And in type 1, this kind of a behavior is not seen. So in mixed state, basically, initially the superconducting, if this is a superconducting sample, then all the field lines would just being repelled by the superconducting material like this. If you draw the field lines like this, so then it will be actually repelled by the superconductor like this thing. So this is the field lines, let's say. but the mixed state, that is Hc, between Hc1 and Hc2, there some change happens. That this is, if this is a superconducting sample as before, now there are small regimes where the flux is able to enter or penetrate through, and around those points, because this is the normal part among the superconducting background, so there will be a critical like there will be a screening current that will be circulating around those points. So because of that, these are like whirlpool of currents around those normal metal regimes, and these are known as vortices. Because now if you draw the field lines are initially like this, right? So they are being repelled out and blocked out completely from the superconductor, but now the field lines can penetrate or enter through these normal metallic regimes. Okay, so this is roughly a drawing, so just consider it like the field lines are being able to penetrate through these normal metallic regimes. So these normal metallic regimes surrounded in the superconducting background is known as vortices, and that is why this state is called mixed state. So normally for type 1 superconductor, when nothing is mentioned, we have to assume the system is type 1. So in the question, this option is not valid, that the type 1 material cannot have a mixed normal superconducting state above the critical magnetic field Hc. Okay, so this is number 3 is incorrect. Number 4 is that a material transforms from a superconducting state to an insulating state above Hc. This is also not correct, because above Hc, when you cross Hc, you go from a superconductor to a normal conductor, not an insulating state. So this is also, this is also false. Only option number 2 is right. So this is also done. Then question number 10 says that the energy gap in a superconductor is maximum at 1 critical temperature, 2 above critical temperature, 3 below critical temperature, and 4 is at 0 Kelvin. So you choose 0 Kelvin to be the correct answer. That is because the superconducting gap actually measures how strong the superconductivity is still in the system. So normally, if you increase the temperature, that means you are basically kind of trying to destroy the superconductivity. And as you are approaching the critical point temperature Tc, that means you are actually transforming into a normal metallic regime. So their superconductivity is completely lost, so there will be no energy gap beyond Tc. So the only temperature where the superconductivity is the strongest or the most dominant is the lowest temperature possible, which is at 0 Kelvin, and that is the temperature at which the maximum value of the energy gap is possible from a superconductor, because then it is deep inside the superconducting state. That is why its gap value will also be maximum. So these are the 10 questions that are given in the assignment of this tutorial 6. Then just as I said, that if you want to kind of solve a mathematical question based on the Lorentz equation, then we can do that. So we solve an extra question. I'll write down the question that we have, and okay, so we have a plate which is taken like this, in this shape. So this is the plate, this is the z-axis, this is the magnetic field direction, this is your superconducting plate, and outside this is the vacuum area. This is the z direction, that is parallel to the edge of the superconducting plate, and this direction is the x direction. Okay. and it can go up to infinity. So this is not bound anywhere. So this is one side edge is seen, but the other side is tends to infinity for the superconducting plate. Okay, so if that is the case, then you have to find out that if the superconducting plate is taken to be like in this case in an xz plane, and the external magnetic field that is applied on the superconducting plate is along the z direction, then you have to find out what is the magnetic field or magnetic flux basically that is present as you move towards the x direction and go inside the superconductor. So basically, ideally, you know that when you are deep inside a superconductor, there is no magnetic flux that is to be allowed. So ideally, deep inside a superconductor, the magnetic flux component should have been 0. But also this is true that when you are applying a magnetic field and if you have a superconductor, so the magnetic field will have a certain penetration depth inside the superconductor, which will be very very small in the nanometer region, and then it will be completely destroying to or decaying out to 0. So that is what we can also see from using the mathematics of London's equation. So we'll try doing that. So the question is that we have an infinite superconducting plate in xz plane where the length along the x cap direction goes till infinity. Okay. Now an external magnetic field B vector is applied on it along z direction, that is it is parallel to the one edge of the superconductor. Now we have to calculate the magnetic flux varying along the x direction inside the superconducting plate. So this is what you have to calculate. So first of all, we have to use the basic London's equation. So we know that the basic London equation gives you curl of J equal to minus n squared by m v vector. So this is the London's equation of superconductor. So this is the main equation that we have to begin with. Okay. Now we can use the formula that your curl of B is the magnetic flux, is equal to mu naught J, where J is the current density. Then your curl of, take curl on both the sides, equal to mu naught, this is the constant, into curl of J. Also this, if you use the vector algebra, vector calculus idea, and you can decompose this part as like this. Okay. So because this divergence of the magnetic flux is 0, so we are only left with this term, which is nothing but minus Laplacian of or grad square B equal to mu naught. Curl of J we can replace by this term now, which is minus n squared by m b vector. Now there is minus on both the sides, so minus will be cancelled out, and you have only grad square B equal to n square mu naught by m b vector. Now we assume that this equal to 1 by lambda square into b vector, where your lambda squared equal to m by n square mu naught, or lambda equal to root over of m by n square mu naught. So you assign lambda like this. This lambda is known as superconducting penetration depth. So this is the effective length scale or depth inside the superconductor starting from the edge of the superconductor up to which the magnetic flux can effectively enter inside the superconductor. Beyond this point, the flux that is penetrating the superconductor will be decaying off to zero. Okay. So superconducting penetration depth is the maximum effective distance from an edge of a superconductor up to which the magnetic flux can penetrate inside the superconductor before the flux density B decays out to be 0. Alright. So if you are to use this expression, then because we are only taking variation along the x-axis, because we have to find out how is the B that is changing inside the superconductor as a function of x. So the spatial gradient that is present in this Laplacian gradient form will only be taken with respect to the x as a variable, as the independent variable. So your that square B can be just written as del to B d2b dx2, because the other variables are not important in this case, so the only independent variable is x. So it is d2b dx2 equal to 1 by lambda square b. Or you know that this kind of an expression has a standard solution, this kind of an expression, where lambda is in this case a constant. So in this case the standard solution is like this: bx equal to somewhat like a e to the power of kx plus b e to the power of minus kx. If your expression is like this, d2b dx2 equal to k squared b. Here your k equals 1 by lambda. That is what gives us bx nearly equal to a to the power of x by lambda plus b to the power of minus x by lambda. So this is the general solution of how the magnetic flux will look like along the x direction if you follow the London's equation. So this is the general solution. Now to get the exact solution inside the superconductor, the value of bx, you have to apply some boundary condition. To get the exact solution, we need to apply specific boundary conditions, right? So the first condition, if you say, is that condition 1 is that as x tends to infinity, the bx should tend to 0. This is valid because you can see from this picture that as you go towards x tends to infinity, that means you are moving deeper inside the superconductor. So when it is at infinity, that means we can guarantee that that we are deepest inside the superconducting phase, and that we know that when it is in a pure superconducting state or deepmost in the superconducting state, then the magnetic flux should be vanished inside the system. So that is why we can write the boundary condition that at x tends to infinity, bx should tend to 0. That means a to the power of x by lambda plus b to the power of minus x by lambda, this will be 0 at x tends to infinity. That means a to the power of infinity plus b e to the power of minus infinity, this should tend to 0. So we know that the e to the power minus infinity is again 0, so this term again makes it 0. But e to the power of infinity actually goes to infinity. So if this term is present, so then the whole term can never be decaying to 0 at x tends to infinity. So to avoid this whole term tend to infinity and not tend to 0. To avoid this, we need to set the coefficient a to be 0. If that is the case, then bx is simply b e to the power of minus x by lambda. With this term vanish now because a is tending to 0. A is equal to 0 by the boundary condition. Now there is a second boundary condition, which is condition number 2, which says that your field value is the constant field that is applied on the superconductor just right at the edge of the superconductor. That means if you have a field along the z-axis, so the field is along the z-axis, then you can have a magnitude part and a directional unit vector. So the unit vector is z cap because it is along the z direction, but the magnitude of the field is fixed, which is b naught, which is the maximum magnitude of the b that is applied. So right at this edge of the superconductor, this left edge, if you think of it, so this is your, let's say, x equal to 0 and this is tending to x tends to infinity. So x equal to 0 is your starting position, and at x equal to 0 the left edge of the superconductor is sitting. So you know that right outside this edge, right at x equal to 0 position, there is a boundary between superconductor and normal material, which is this vacuum in this case, and there the field value will be the maximum magnitude that is applied, which is b naught. And then as you move inside the superconductor, some part of the field will be able to penetrate, but that value will be decaying off from the maximum value b naught. Only at the boundary at x equal to 0, at boundary x equal to 0 or left edge also of superconductor, before penetrating inside, the magnetic field has the maximum magnitude b naught. Or this expression you use and put x to be 0. That means it is b e to the power of 0, which is 1, equal to b naught. Or in other terms, your constant b value is nothing but your maximum field magnitude, that is capital B. So the whole expression now becomes bx equal to b naught as the constant to the power of minus x by lambda. So this is your final expression. This goes as if that initially magnitude was very the highest, that is b naught at x equal to 0. So b naught at x equal to 0. As gradually x increases, b decreases exponentially. So it falls down or decays exponentially because there is this e to the power of minus x by lambda form. So as you increase x, this will decrease. Finally, at x equal to lambda, when the x-axis distance inside the superconductor is of the order of the superconducting penetration depth, then you can say your b is actually tending to a very small value or almost tending to 0, because x equal to lambda, it becomes b naught e to the power of minus 1 or b naught by e, which is a very small value, and finally it can be effectively decaying down to 0 when it is deep inside the superconductor and beyond the penetration depth of the superconductor. So basically the thing goes like this, as we can expect from the physics of superconductor also, that initially the magnitude is, let's say, b at the edge, but then as it tries to penetrate a little bit inside the superconductor, so it falls up exponentially like this, 1 minus x by lambda, exponential fall. And then up to lambda is basically, up to lambda is somehow the effective length scale, which is the penetration depth of the superconductor, is up to which this has a still finite value, and then beyond this point the magnetic flux, even it is present, but the value is so small that we can almost say that in deep inside the superconductor the magnetic flux cannot penetrate anymore, because superconductors are perfect diamagnets, so it decays down to 0. So in this case inside B equal to 0. Only this effective length scale up to this is called the superconducting penetration depth, and the value is in the order of 10 to 100 nanometer. So by this idea we have been able to actually calculate what is the behavior of the magnetic flux density inside the superconductor under applying these boundary conditions for this typical particular system. Okay, so with this we have finished the total tutorial on superconductivity for this week. So for the next week's tutorial we will solve the next week assignment then.